construction. So let's see if we can demystify this idea of an eigenvalue. Right? So let me just reiterate. What we're doing when we multiply a matrix by a vector is basically linearly transforming that vector, right? Remember, the resultant vector is some sort of linear transformation dependent on that matrix. So we've got this vector and we've got this matrix, our spurious covariance matrix. So the eigenvectors and eigenvalues represent the axes and the size of the transformation somehow, right? So we end up with these eigenvectors, and they're informative in that we know that the first eigenvector is in fact an axis that goes through that data cloud, right? That describes most of the variation, and that we can in our data cloud. Right? So what is an eigenvector? Well, let's have a look at a matrix. This is the matrix here, 2, 1, 1, 2. Okay, and let's say we have some points. These are all the original points, right? If we multiply those points by the matrix, what happens? Right? Original data, multiply it by the matrix, and that's my matrix impersonation. We get things shifted, right? But as we know, the matrix has acted to linearly transform the data, so it's now sitting in a slightly different position, right? So we look at these points. So this point here, what happens? That ends up here, right? This point down, wait for it to get back. It's down here. That ends about here. There, something like there, right? So what happens? Let's have a look at some vectors. Right, let's grab some vectors here. Some of them do not change direction. Some of them do. Look at the red vectors, vertically up and down. What happens to them? They get transformed, so they're sitting in a different direction now, right? Right? Which vectors don't change direction? Blue, that's right. What else? Pink. Neither the blue nor the pink vectors here, see, after the transformation of the matrix, those data points, or the vectors describing those data points, are still in the same direction. They might have been changed in how long they are, but they're still lying in the same direction. That is in fact what an eigenvector is. It is a vector that is invariant under the matrix transformation. Okay, I think I can pretty much say it here. Which vectors don't change? The answer is the blue vector, which is pointing in the 1, 1 direction, right? 1 to 1, going that way. And the pink direction, which is 1, negative 1, or the inverse of that. So this is the same vector. It goes going that way or going that way. Sorry, that way or that way is the same thing, right? Those are in fact the two eigenvectors for the matrix 2, 1, 1, 2. Okay. So what happens to the blue matrix? The blue vector. The blue vector changes length, doesn't it? It gets 3 times longer. Its eigenvalue is in fact 3. The pink vectors are not changing in their length, so their eigenvalue is 1. It's invariant. Right, so the eigenvalue, you already know what an eigenvalue is, right? How did we define it at this point in time with respect to a variance-covariance matrix? What does it describe? Can you remember?
Total variation.
The total variation once you project the data points onto that, right? Onto that axis. It's the variation of the data points onto that axis, right? And we know essentially what the eigenvector is. It's sort of how it's transformed by the matrix, how the data points have been transformed by the matrix. Okay, so eigenvalues, we know what it is. It's intuitively we know what it is when applied to a variance-covariance matrix, right? They can represent the consolidated variance of the square matrix, or the variance accounted for by that particular axis, the linear combinations of the variables, right? So that's what I said here. The eigenvalue describes the variance of each axis in an orthogonal basis. So the eigenvectors are the orthogonal basis. The eigenvalues is the amount of variation if we project the data on that. Okay, so let's think back to this thing that we did before, which was this matrix here, 1, 1, negative 2, 4, right? And remember we had this example here. This is the original vectors denoted by the red circle, right? So you can think of any arrow pointing to any point on that red circle, and that gets transformed by the matrix A, if we multiply it by the matrix A, to lie then on this blue ellipse, right? So those eigenvectors we now know are those vectors which, when we multiply it by the matrix A, still are in the same direction, right? In other words, those vectors x, where if we multiply that vector by A, is in the same direction, it's just, it might have changed length. So it's still x, but it's just x multiplied by some sort of scalar. It could be x by 3, or negative 1, or something like that, right? Okay, so let me give you a couple of examples. Let's choose some vectors, and we will see whether or not they are an eigenvector if we multiply, for the matrix A. Okay, so if we go 1, 0, so that's 1 here and 0, right? Where does that end up? We end up, if we multiply by the matrix, to this point here. So this is the original vector, and this is the direction that it ends up in here, right? So that's clearly not an eigenvector because it's not in the same direction. How about 0, 1? Here, pointing up, right? After we multiply it by the eigenvector, we end up with negative 2, here 4. So that's where we end up with, that's the relative point. So that's clearly not in the same direction, right? Negative 1, 0. Negative 1, 0, this one here. Where does that end up? Negative 1, down here, right? So that is in a different direction. How about negative 0.71, positive 0.71? That's this one here, right? After you multiply it by the matrix, you end up here. In fact, it leads you to negative 2.1, 2.1, right? Which is just 3 times what it originally was, right? Just 3 times negative 0.7.71 leads us to this. So this is an eigenvector because it's in the same direction. It's a different length, but it is in the same direction. It's just a linear combination of the original, a scalar combination, in fact, of the original variable, a scalar multiple of the original variable. Does that make sense? Right? So those eigenvectors are those vectors where once you multiply by the matrix A, are still in the same direction. Right? They'll change length, but they're still in the same direction. Right? In fact, there's another one, and that is negative 1.8, so that's going to be here, 0.89. So this is the second eigenvector, right? Because if you multiply that by the matrix A, you end up with, negative 0.89, 0.45, this is the one here. You end up with this thing here, which is in the same direction, and in fact, the resultant vector is just double what it originally is. So the eigenvalue is 2. Yeah. So the eigenvalue for the first one, this is the eigenvector, negative 0.71, 0.71, right? The eigenvalue associated with that, because every eigenvector will have a value associated with it, an eigenvalue, is 3. So the eigenvalue is 3 for this vector here, and the eigenvalue is 2, I don't know if you can see that very easily, for this vector here, right? Because it's doubled in length. Right, so eigenvectors are also known as characteristic vectors, right? So with respect to variance-covariance matrices, it is a non-zero vector that forms a new axis, right? And we're going to use it to relate the new axis to the original variables. And we actually, although we've got these new eigenvectors, right, from our matrix, we could arrange them in whatever order we like. We have chosen to arrange them such that the biggest eigenvalue is called axis 1, that's PC1. The second biggest will be PC2, and so on and so forth. Okay? So if a matrix A is of size P by P, it has P eigenvalues. So eigenvalues can have values less than or equal to 0. And they're not unique, right? So you can have negative eigenvalues. You can have the same eigenvalue, in fact. Negative eigenvalues are a problem. They're not usually a problem with what we're going to deal with. It's when you start dealing with non-Euclidean data and start dealing with different non-Euclidean spaces that they become a little bit more problematic. Okay, so I'll stop there. I'm going to talk a little bit more, quite a lot more about this and try and explain what's going on with these eigenvectors and eigenvalues with respect to the variance-covariance matrix. But before we do that, or should I do that now? Why don't I start that now, actually? Because I don't want to end up talking at you guys at 5 o'clock, right? I mean, near then, because you all will be asleep. And so will I. Yeah, that's how I feel about it too. Okay, so I'll just talk to you for a little bit longer, given that you're still awake. Okay. Right, so we can write this, right? We know that if we have a vector and we multiply it by the matrix A, it's going to equal, if it's an eigenvector, if basically we end up with the same vector, but it might be of different length, and that length is determined by the scalar lambda, which is the eigenvalue, right? That's what we've just shown you. It's an eigenvector of matrix A if you end up, the resultant vector that comes out of it is in the same direction. So it's still e to the k. This is still just the vector, right? And this is just the size of the vector, the lambda, right? So A has got to be some sort of symmetric matrix, typically, right? And lambda is a scalar, and we know that's the eigenvalue. Right? So what we know, A times E is equal to lambda times E. So A times E is a scalar multiple of the vector E, right? And that scalar is this value here. Okay, so that's what we're saying here, in this example here. Right, so to find the eigenvalues, if these two things are the same, if A times the eigenvector is equal to lambda times the eigenvector, then if I just subtract this from this, I'll get 0, right? Because these two things are the same. So this minus that is going to equal 0. Right, so this is an equation I can use to try and find the actual eigenvector, what e to the k, e sub k is. I just call it eigenvector, sorry. So another way of stating this is saying, hey, look, well, both of these things have got the eigenvector, so I can take that outside the brackets. And so I've got A minus lambda. Well, I need the identity matrix in here. So lambda times the identity is just lambda, right? So it's all on the same footing. So these two things are the same thing. And this is what I'm going to try and solve, in fact. Right? So for lambda to be an eigenvalue, there has to be, that's what we're going to solve first. The eigenvalues, there must be a non-zero solution for e to this following equation, right? A minus lambda I, all multiplied by the eigenvector. Right? This is only going to occur if the determinant of this is equal to 0. Right? Because we know that the vector has to be a linear combination of this, doesn't it? So that means the determinant is going to be 0. Right? So we want to find a vector, essentially, that's going to give this equation, make that equal 0. Okay. So this equation is known as the characteristic equation, right? A minus lambda identity, the determinant of that is equal to 0, because that's what we're going to use to find our lambdas, our eigenvalues. So just to reconfirm, this is the eigenvalue. This is what we're going to find first, right? We've got a 3 by 3 matrix. There will be 3 of these, right, that we can find. And this is sometimes called the characteristic root, or the characteristic value. Right, so let's give you an example. Let's actually break down the math. Let's say we have a matrix. It is square and it's symmetric, right? And it's let's say it's a covariance matrix. 9, 6, -2 on the off diagonals, right? This is the identity matrix. It's always just ones on the diagonals and zeros everywhere else, right? And this is what we're trying to solve. So what is that? That's saying, well, what's A? A is this matrix here. Minus lambda times I. Well, that's just lambda on the diagonals, right? Lambda times this is just going to end up with the lambdas here, right? And the zeros everywhere else. So this minus this is equal to 0. Or the determinant of that is equal to 0. Basically. So what does this end up being? Well, what have we got? We've got 9 minus lambda minus 2, right? We know how to subtract matrices, right? 9 minus lambda, -2 minus 0, right? So this is 9 minus lambda, and that's just -2. Minus 2 minus 0, and this is going to be 6 minus lambda, right? So this is what we've learned. It's literally just the subtraction that we know, subtraction of all the elements within that, and we know that if the determinant of that is equal to 0, for whatever lambda we get, then we've got an eigenvalue. Right? So what is this? How do we calculate the determinant of a 2 by 2 matrix? You guys remember? You multiply those diagonals together, you subtract one from the other, right? So let's multiply these guys together, and we're going to be subtracting this from it, right? 9 minus lambda times 6 minus lambda. Damn it, quadratic equations, right? You thought that was the last time in Form 4 or whatever year, what do they call it now, year 17? You'd have to do it, but you got to do it once more. We end up with a quadratic equation, 9 minus lambda times 6 minus lambda, and then we've got this minus 4 bit here that we have to do for the determinant. So this is the equation for the determinant, right? And we know that if that's equal to 0, we can find values of lambda that make that equal to 0. Those values of lambda are going to be the eigenvalues. So let's expand that, right? Well, what do we get? We've got a 9 times 6, 9 times negative lambda, and negative lambda times 6, negative lambda squared, right? So the 9 times 6 is 54, but then we've also got a minus 4 on there, so that makes it 50. We've got a lambda squared in there, and then we've got what? We've got a 9 lambda, a negative 9 lambda, and a negative 6 lambda, right? 9 times negative lambda times 6. So that makes the 15 lambda here. So we end up with lambda squared minus 15 lambda plus 50 equals 0, right? And you got to solve this. It's a quadratic equation. You're going to end up with 2 answers, right, for lambda. Right? So when is that equal to 0? What values of lambda will give a value of 0? Right? 5 and 10. Right? So we know that those are the eigenvalues. That's the solution. And I haven't got it in the assignment. We haven't done it for assignment 1, so I'll put it in the exam instead, basically. That's the good news. You don't have to do it for assignment 1. Yeah. So that's how you calculate essentially the eigenvalues for a 2 by 2 matrix. Of course, you never do this by hand. That's why I'm not good for the assignment, really. And I'm an asshole for putting it in the exam, but I may do anyway, because I haven't written it. But you would never do this by hand if there was more than 2 by 2. In fact, you would never do it by hand, right? You just get the computer to calculate it. Okay, so there are as many solutions as there will be dimensions in A, in your variance-covariance matrix. So you're doing this for a variance-covariance matrix, right? So if this matrix was 3 by 3, you'd end up with a cubic here. And so you'd have 3 things that are multiplying together, and so you get 3 possible lambdas that would give you a solution that was equal to 0, right? So you end up, it becomes, obviously you wouldn't do this by hand, and there are some very quick computational ways of doing it that are much faster than you trying to do it by hand. So you don't really have to worry too much about it. Okay, so let's talk about eigenvalues a bit more, right? So for any square matrix X, right, it will have P eigenvalues. So that's a square matrix. That means it's P by P, right? The sum of all those will be the trace of X. The sum of all the lambdas that you get will be the trace of X. right? So what does that mean? If that is a variance-covariance matrix, right, what have we got as the trace of x? If x is the variance-covariance matrix, what have we got down the diagonal? Remember, the trace is the diagonal? And what are those elements along the diagonal? They're not one for, well, they're not necessarily one for a variance-covariance matrix. They are the variances, right? The variance of, so if we have your variance-covariance matrix, I'll call it sigma, because it's the population. Let's say it's 3 by 3. We might have, 7, 2, 4, and then we have, negative 15, blah, 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 blah. This is the variance of variable x1. That's the variance of variable x2. That's the variance of variable x3, right? These are the variances. And these are the covariances of these things, right? So for a variance-covariance matrix, if you are doing an eigenvalue deconstruction of that, the trace is the sum of all the variances, the total amount of variation with respect to each of the individual variances, right? That's going to equal, in fact, when you do the eigenvalue deconstruction, your lambdas will sum to the same value as your trace, right? And the product of the lambdas is going to be equal to the determinant of x. Okay, so this is probably more useful, obviously, if when we've been doing it in SAS, we haven't been doing it typically on the variance-covariance matrix. That's not usually what you do. Usually, you do it on the correlation matrix, R. Right? And this is just a value of 1 down the diagonal. Right? So remember, what was the sum? So that would mean that the sum of these is just what is going to be p, isn't it? So remember, the average eigenvalue is of size 1 then. Right? Because the sum of all the eigenvalues is just the sum of, is just going to equal to however many elements there are. So eigenvalues bigger than 1 are basically explaining more than you would expect by chance. Values less are explaining less than by chance. Right, so some properties of eigenvalues. If the eigenvalues of a matrix are all positive, then the matrix is called positive definite. If the eigenvalues of a matrix are all non-zero, then the matrix is called is of full rank. In other words, we can invert the matrix, it's non-singular, and we can do a proper eigenvalue decomposition on it. If the eigenvalues contain at least 1 0, then actually we can't invert that matrix. There's no true inverse, right? And SAS, or whatever is trying to calculate the inverse, if we need to do it, has to do something else. It has to calculate a generalized inverse instead. Right? That's the main thing. Sometimes, with some matrices, you get eigenvalues that are both positive and negative. We're not going to talk about that in this course. It happens with funky distances and non-Euclidean data, right? Which is relevant to biologists who will use all these distances. We'll talk about distances in the second block, and distance matrices. And then you can get, with these non-Euclidean distances, with what's called the triangle inequality is not held, then you end up with some problems, and you get negative eigenvalues. People have thought of ways to get around this, but essentially they just try and ignore it and pretend that it didn't happen. Right, so the number of lambdas you get equals the numbers of dimensions, the number of non-zero lambdas that you get, I should really say, really equal the number of dimensions of your matrix that you've got. Right? I say the number of lambdas because some lambdas can be 0, and in theory some can be negative. Right? So once you know the lambdas, you can then solve for x in this using this equation, because we know this is true, right? A times x is equal to lambda times x, to find the eigenvector. Right? So the solution, when you do it, if you have to do it by hand, some poor sucker makes you do it by hand, is to find the eigenvalues first, and then substitute those values into the equation to find what the eigenvectors are. Right? So, we'll stop I guess what's important? What's important is this idea that what is your correlation or your covariance matrix doing? It's taking your data. What it's doing is, given any data, it's transforming that, so it's gonna have a shape that is basically like your data cloud, right? So let's say we start with random data there. If we then run it through your variance covariance matrix, sigma, right? It starts shifting data like this and like this and like this and like this, etc. Right? And those vectors that don't change are going to be the ones that actually are describing the amount of variation, because in fact your matrix is a matrix about variation. Right? So those vectors really are a variance covariance matrix is a matrix that acts to rotate and elongate. I forget the term. Elongate your data, right? So the rotation and elongation is gonna. You want to find a vector that remains invariant. It's going to be those ones that describe the most amount of variation in the data, right? So that's sort of how it all ties together. Okay, so before we carry on with the math, some examples of that. We'll go back into normal space. Before we actually calculate the eigenvectors, we'll actually go and do lab 4. And once we do lab 4, I will show you the results of the movie data set that we've got. So here are the results. Sorry, here's the data that we've got for the movie data set. We've got everybody in here. Nick is the last one. Beck, Yang, Juliet, okay, Jamie. Right. So we're gonna basically recreate what you do in lab 4, which is create a biplot, or what SAS calls a multi-dimensional preference plot, to see how your preferences lie with respect to each other, and see where the movies lie with respect to that. Right. So that in this case, we're going to say the movies are the data, are the cases, and your preferences are the variables. So the resultant plot, every person will have a vector, right? And we will see how well that is described. We'll see how well the plot actually describes your preference. Okay, so go ahead and do lab 4.
But all those inputs are not needed.
Doesn't require it to be in
Oh, I thought the multiplier analysis, the unit has to be observations for variables.
Oh, you mean the actual cases themselves have to be independent of one another.
Oh, yeah.
We have a ranking here. It doesn't really, on average, the ranking doesn't matter. The fact that this is 13 doesn't mean that this one is also going to be close to 13 or not, right? So they are independent of one another in that respect.
Okay, so in this case, variables are not.
Yeah.
Okay.
Yeah, with variables.